All right, welcome back. Today we're going to be talking about things called Atwood machines, but really what these actually are connected objects. So the scenario where two objects are connected by a string to each other. They could be connected by a string, they could just be touching each other and pushing each other. So like this, two objects right next to each other, that would be 1 and 2. And I'm just pushing on them, right? Pushing on those two objects. Or I could be pulling this object with a string. All sorts of scenarios. But if two objects are connected, here's the most important thing that you should know. First, they must be accelerating at the same rate. They're connected. These two objects are connected, so where one goes, the other has to go. How fast one goes, the other has to go that same speed. If one's at rest, the other one has to be at rest because they're connected. You can't have one object that's flying off accelerating at 10 meters per second squared, and this one's at rest. No, they're attached. They're going to go together, right? It's like when you're in your car. You don't get to stay where you're currently located. If your car starts accelerating, you go with it because you're a connected object. So all connected objects have to be moving with the same acceleration. That's the most important thing when it comes to connected objects, right? The second thing we're going to start talking about is this idea of connected objects as a system. Since everything that's touching each other, these two objects or these two objects are connected and have to be accelerating at the same rate, either 0 or some other acceleration, that means that they're acting as a system. I can treat them as one object. I'm allowed to treat multiple things as one object if they're moving at the same rate, if they're moving together, which connected objects are, right? We just defined that. We said that's the most important thing about connected objects is that they have to go at the same rate. They have to accelerate at the same rate or move at the same rate or stay at rest together. So we can treat connected objects as a system. So let's try that. I'm going to draw the free body diagram for this system. So this is 1 and 2. Before I do that, I'm going to draw the free body diagram of both individual objects. So I'm going to say this is the free body diagram for 2. This is the free body diagram for 1. So for 2, it's on Earth, so it's got gravity. It's not on an inclined plane, so it's still just FG, right? We watched the last video. We know on ramps, it's FG cosine theta. This is a flat ground. It's good. Going up, it's got Fn, because again, flat surface. And it's being pulled on. This is the force of 1 on 2. Oh, I did that wrong. 1 on 2. Because it's being pulled on. That's the only thing touching it. We're going to assume for right this second that it's frictionless. We'll do a friction example in a second. For object 1, it has the force of 2 on 1 because 2 is pulling on it this direction, right? They're connected by a string. So whatever 1 is pulling on 2 with, 2 must also be pulling on 1 with. It's also being pulled by this string over here, some force of tension. And of course, it's got, I'm never going to forget, gravity and Fn. So here's the deal with the system. When we write out a free body diagram for the whole system, we only care about the direction where it's actually accelerating. So in our case, both of these are not accelerating up and down, so I only care about this direction. I only care about the horizontal forces on the system. Now, as I go through different connected objects today and I get to these funky things called Atwood machines, that direction is going to look weird. But trust me, all right, we're going to work through the process. So in this case, The only way these two objects are going to accelerate is left and right. So I only care about, when I draw the free body diagram of the system, things that are going left and right. Okay, because again, they're resting on ground. They're not going up and down. We don't have to worry about that. So when I draw a free body diagram for the system, I label it system so that I know it's a free body diagram for the whole system. And then I'm going to just look at all the forces acting on my objects inside of the system. So on 2, there's nothing going to the left, no shoes there. On 2 to the right, I have the force of 1 on 2. Well, the force of 1 on 2 is the action-reaction pair to the force of 2 on 1. I'll highlight these in green. These two forces are actually an action-reaction pair. They cancel each other out completely. One's going to the right, one's going to the left. They completely cancel each other out. So they aren't going to show up on my system because they completely cancel each other out. So forces between objects in the system don't count, right? It's just like whenever I had just a single object as my free body diagram, any forces within that object didn't get counted. All of my body parts are pushing on other body parts, but you didn't draw that on a free body diagram because it's all connected. They're all action-reaction pairs within me as a system, and so you didn't have to put them on the free body diagram. Same thing with this system of multiple objects. If there are things that are action-reaction pairs and cancel out, don't draw them on the system. This is going to take practice. This is why we're going to go through the steps of drawing both free body diagrams, the system free body diagram, and then going from there. Okay? Trust the process. So, both of these forces are out, so I don't care about them. The only force remaining on my whole system is just this force of tension. So if I write out an F net for my system, it would just have this force of tension from this rope. This force of tension right here. Somebody's pulling on these guys to the right. And that's it. Now, since this is a free body diagram and an F net equation for the entire system, when I write out that it's accelerating, so it has mass and acceleration, I need to make sure I include the mass of everything in the system. So, a new thing with connected objects. When I have connected objects, I'm not only going to create the free body diagrams of both individual objects. This is something you will start with. As you get better and better at connected objects, you probably will eventually skip this step. Not yet, not tomorrow, but maybe the day before the test. Honestly, maybe try when you get to me in Physics C. Draw both free body diagrams, draw the system free body diagram, and then write out the system F net equation and most likely solve. I'm going to write this on that side of the board, the steps for solving a connected object problem. 99.9% of the time, you are going to need to find the acceleration of the system first. You cannot find the acceleration of either of those objects first. Here's why. If I look at object 2 and write its F net equation, it only has this force of 1 on 2. I don't know what that is. I know that this object's accelerating, so I have MA equals that. I have 2 unknowns. If I draw out this F net equation for 1, it would be equal to Ft minus F2 on 1, which I still don't know. Even if I know Ft, now I've set MA is equal to Ft minus F2 on 1. I again have 2 things I don't know. So I can't solve either individual free body diagram or F net equation by themselves. That is why we go through this process. If you write out the system, those 2 unknown forces went away. Now, it's only one force that you probably know in this unknown, and you can solve. So I'm going to write this over here in red so that you understand. When solving connected object questions, first, draw each object's free body diagram. You're going to do this as you start with these types of questions. Eventually, you will get to stop doing that step because you'll understand how these work. But for now, do that step. Step 2, draw a free body diagram of the system. Step 3, write an F-net for the system. And 99% of the time, step 4 is going to be solve for the system's acceleration. Fifth and final step, go back and solve individual free body diagrams. That's, none of those are letters. Free body diagram or F-net. So oftentimes, the way a connected objects problem is going to work is they're going to say, okay, here are these connected objects. What is the force of tension on box 1? Or what is the acceleration of box 2? Or what is, if this was frictioned, what is the friction on object 2? Right? They're going to ask some specific question about one of the objects, most likely. Not all the time, but a lot of them. You still start by drawing both free body diagrams if needed, so that you can draw the system free body diagram and get the system acceleration. Because 99.9% of the time, they are only going to give you the information you need to solve for the system acceleration. You will be missing some forces, and you will not be able to automatically solve a free body diagram for an individual piece of this larger system. Okay? So, for example, if the question for this scenario, it's frictionless connected objects, if the question was, what is the tension on object 1? So, my example, what is the tension on block 1 from block 2? Block 1 has mass 3 kilograms. Block 2 has mass 5 kilograms. And block 1 is being pulled with 100 newtons of force. So, to answer this question, I've done a lot of the steps. I drew my original free body diagrams for each individual object so that I could draw the system free body diagram. You're going to see me do that for several examples in the rest of this video. Then, from the system, I wrote out my F-net for the whole system. And now I'm going to solve. So the first thing I'm going to find is this system acceleration. I have everything I need. So the mass of block 1 was 3 kilograms. The mass of block 2 is 5 kilograms. I'm looking for acceleration, and my force was 100. So I get 8A is equal to 100. That works out to be 25 divided by 2, so 12.5 meters per second squared. So I've done all the steps through 4. Now I'm going to go back and use a single object's free body diagram to find the answer. Now, for this, it's asking for what is the tension on block 1 from block 2? So it's asking for a force on block 1. But remember, the tension in that string is the same everywhere, right? It's an action-reaction pair. However strong 1 pulls on 2, 2 will pull on 1. So it doesn't matter which one I solve for. I can solve for the tension on 2 or on 1. It doesn't matter. I personally am going to choose 2. Why, Miss Limer? Well, remember the original free body diagrams? How many forces are acting on block 1? 2. Ft and the tension for block 2. How many forces are acting on block 2? 1. Just the tension from block 1. So this is a trick I do with connected objects. If I'm going back and solving for something that's on both blocks or both objects, I always choose to solve using the one with less forces acting on it. Does it matter? No. Could you get the answer either way? Yes. So truly does not matter. But what I'm going to do is I'm going to say, okay, I don't know why I'm doing that with my hand. The free body diagram for 2 is Fg, Fn, and the force of 1 on 2. So the F net is mass of block 2 times acceleration is equal to the force of 1 on 2. Mass for block 2 is 5, acceleration is 12.5. So that's 62.5. I hope that's right. So that's the force of tension. Technically, this time it's of block 1 on block 2. But we were asked for block 1 from block 2, but that's an action-reaction pair, so they're the same force. Cool. All right, let's see our first Atwood machine. So this could have friction on it, right? If there was friction, guess what? There's friction on both blocks. So when I draw the free body diagrams for both blocks, there would be friction on both of them. And so then when I draw my system free body diagram, there should be friction from both blocks. So there should be 2 forces of friction on my system. We'll go over an example in class and I'll show you. Well, let's spend the rest of our time talking about Atwood machines. An Atwood machine involves a pulley. That's the idea. This is what a traditional Atwood machine looks like. Block 1, block 2. This up here would be a pulley. Now every question is going to say the exact same thing. It's going to say that these 2 objects are connected by a massless string. We talked about tension. We talked about ideal strings. So this isn't an ideal string, so no worries. Second, it's going to say that's a massless pulley with no friction. That's important. If it was a massed pulley with friction, everything got way more complicated. It is not. So you don't have to worry about any extra stuff. When we get to rotational dynamics, there'll be extra stuff. But for today, massless string, massless pulley, no friction. Awesome. So what I'm going to do is I'm going to draw the free body diagram for each object. So 1 has force of tension going up, and we'll call it M1G going down. That's just so I know what they are. Who's who? Block 2 has force of tension going up and M2G going down, right? Those are the free body diagrams for these 2 objects separately. So now I want to draw a system. So I have to decide which direction is going to be which. I will say this, my favorite way to do this is that this is my negative y direction. So I kind of visualize these as just one string pulled straight up. So it looks like this, 1 and then 2, right? That's what I'm saying. I'm saying that I'm going to consider this system, I have to consider one direction through this system. So anything that's going up, and then on this side, anything that's going down, those are going to count as my negative y directions. So I'm thinking of these 2 objects like this with their forces M1G Ft Ft M2G. This is going to take a little bit to get used to, but for an Atwood machine, since it's a pulley, and so things are going, both of them are going down, but they're going in opposite directions because they're pulling on each other, right? So you have to decide, okay, on my Atwood machine, this direction is going to be this. Technically, you can make it whatever you want. You could make it negative y, negative x, positive x. It's entirely up to you. The reason I choose negative x is so that I can keep this thing that's going down, going down. I don't typically use the x direction because I don't want to forget that Atwood machines are driven by something moving downward. Okay, that's what's going to happen. We'll see a demo. We saw a demo of this in class, right? I had two masses that are over a pulley. One's going to pull the other one up, right? That's what happens. So to draw the system, all of that to say, here's my system. My system has in the negative y direction M2G. This force of tension is equal to that force of tension, and they're pointing in opposite directions. This one was pointing in the positive y direction. This one is pointing in the negative y direction, so they cancel out. And then, remember, this is my negative y direction, so around this side, going down would be my positive y direction. So that's M1G. And that's the free body diagram for my system. That's the thing that's gonna take time to figure out, okay? From here, I would write out F net y is equal to M1G minus M2G. So that's both masses times the acceleration of the whole system is equal to M1G minus M2G. So the acceleration of my whole system is equal to G times M1 minus M2 over M1 plus M2. For a straight Atwood machine, the simplest kind that you can have, that is the acceleration. This would be the acceleration of the whole system, so both of them. Notice, if mass 1 is bigger, then my acceleration is positive. So I'm going down like this, and this one's going up, and they're both accelerating in the positive direction. If mass 2 is bigger, then this is a negative acceleration, and so now they're both going down in my negative y direction. So whichever mass is bigger, that's the way they're going to go. Makes perfect sense. All right? I'm going to show you one modified Atwood machine, and then we're going to practice this in class. Remember these steps. I draw out the free body diagram for each individual object as needed. Eventually you'll get good at this and you'll be able to jump to here. I definitely write out the free body diagram of the system, write the F net equation, solve for the system acceleration, and if this asks me, hey, what's the tension on block 1, I would go back, use the free body diagram for option 1, and say, okay, well, I know it's acceleration, so I can solve. Don't worry, literally so much practice headed your way in class. All right. That's the simplest Atwood machine you can possibly have. Our favorite thing to do in AP Physics 1 is to modify Atwood machines to make them as wild and crazy as humanly possible. I'm going to start with a very simple modified Atwood machine. It's still an Atwood machine if it still has the pulley, but in this case, I have an object resting on a table. We'll say there's friction, make it complicated, and it is attached to a pulley that has a hanging mass down here. So, first step, I'm going to draw the free body diagram for each object in the system. This is really important, especially for a modified Atwood machine, especially if there's friction. That way I don't miss any of the forces. So, for object 1, it has Fg going down, Fn going up, and it would have a force of friction going this way, and a force of tension going to the right. I know the friction is going that way because it's the only thing that makes sense, right? If this block is heavier, then it's going to have enough tension in the string to hold this block up, no issue. So it won't be moving. So there will be static friction moving, I guess in that question, FT, still that away. If the object's moving and it's actually sliding because this one's big enough, then it's moving that away, and so the friction has to point the opposite direction. There's no scenario, unless somebody starts attaching themselves to this block and pulling on it, that this block is going to go that way. That's not possible. Based on this setup, it can either fall that way or be at rest. Those are the only two options. In both cases, friction's to the left. So that's one. Two has, I'll call this F1G, F2G, and then the force of tension. So as soon as I get these free body diagrams drawn, the first thing I want to do is see what cancels out. So both of these are attached to this rope. The tension is the same in both of them. So these are going to be an action-reaction pair, and they're going to cancel out. No tension on your system free body diagram unless it's something that somebody else is pulling on with. Now I have to decide which direction is going to be what. So even though this isn't a full pulley and it doesn't do the whole U-turn, I still have to say that this is going to be my negative Y direction. That's the way I do it most of the time. If you want that to be your negative X direction or your positive X direction, it's up to you. How you draw this free body diagram will not change the actual answer, so it's fine. But I'm going to say this is my negative Y direction. If it helps on your free body diagrams, draw that direction on there so that you can see, okay, this is what I'm counting as my negative Y direction. I don't care about any forces that aren't going in this direction. It's, again, just like the first one where I said I'm basically pulling these completely taut. I'm saying that that's the direction I'm worried about. I'm lining them up. Even though they're not in one horizontal line, I'm pretending that they are. And I'm saying these are the only things I care about. This is my negative Y direction. It's all one direction, not to quote the band. And that's how I'm going to draw my system free body diagram. So then I draw my system free body diagram. So that means this is pointing not in the negative Y direction. It's pointing in the positive Y direction. I've got FF. That force of tension canceled out. This force of tension canceled out. And then I have going down F2G. Those are the only forces that are on my system. Fn and Fg from block 1 are not in the direction of my system. Block 2 is not pulling them that way. The pulley turns the force of tension, so this is only affecting the horizontal component of 1, right? The pulley changes its direction, but it's still only affecting the horizontal, not the vertical. Now I can write an F net equation. So F net Y is equal to FF minus F2G. So the mass of my whole system is equal to this friction force. I'll say it's at rest. And 2A is equal to mu S Fn. What's the normal force for block 1? This friction came from block 1. Keep track of where things came from because they can have different normal forces. Oh no. Fn, so that's M1G minus M2G. If I say it's at rest, then this side of the equation actually equals 0. And I could solve for maybe the coefficient of static friction. Maybe that's what the question's asking. I could say that the coefficient of static friction is this, and maybe it's asking for what's the maximum mass that M2 can be where it won't pull it over the edge? That could be a question I'm asked. So as a recap, what we talked about today was connected objects. These are objects that share one thing in common, which is they must accelerate at the same rate. Since that's true, a way to solve them without knowing all the information, like what is the tension on each individual string or each individual object, I can draw a free body diagram of the entire system and solve for the acceleration of the system, since they both have to accelerate at the same rate since they are attached. So again, when I'm solving any connected object problem, I am going to draw each object's free body diagram until I get really, really good at this. Then I'm going to draw a free body diagram of the whole system. I'm going to write an F-net equation for the whole system. I'm going to solve for the acceleration of the whole system. Then I'm going to go back and solve for whatever the question actually asked. All right, let's practice in class.